that I'll be doing. I realize you'll only be here for this one, but in case you're interested enough to look at the activities that I've designed for the other sessions as well, you have them at your disposal there. I'm going to be talking about student activities for analyzing data in this session, and then in subsequent sessions, so you know what the rest of the handout is about. I'll be talking about activities for exploring randomness and activities for drawing inferences. And you can see information about me, including email address, so feel free to send questions and comments my way if something occurs to you after this week. I have a web page there which has a link to a website for my workshop statistics project, which has lots of information such as instructors' guides and sample exams and syllabi and data sets and things like that. So if you're interested in perusing any of that, you can start with the web page I've given you there. You can see I actually made it through the whole first page of my handout without an original thought, since I did, title and address and that stuff. And then I decided to quote from two statistics educators who have really influenced my work in working with hands-on activities and things like that. George Cobb, I hate to insult you by reading the quote to you, but the quote is so poetic that I love to read it. Shorn of all subtlety and led naked out of the protective fold of educational research literature, there comes a sheepish little fact. Lectures don't work nearly as well as many of us would like to think. I'd like to be able to tell you that that quote inspired me to develop the kinds of materials and activities that I have, but I can't honestly say that because I didn't discover the quote until I was pretty much done. But I liked it so much that I always talk about that quote. And Joan Garfield, a little less poetic, but really getting at the heart of the matter, arguing that statistics teaching can be more effective if teachers, first of all, determine what it is they want their students to know, and then second of all, design activities designed to induce that kind of performance and knowledge that you're looking for. So I hope that the activities that I'll be going through with you are true to the spirit of those comments. See the back of the first page, the second page. I could spend the whole hour talking about the use of student activities, but that would seem pretty hypocritical. So in another couple minutes here, I'm going to shut up and ask you to start working on some activities. And I'll certainly talk a lot more with you than I do with my students, just because I want to make more efficient use of our time here, and because you already know a lot about statistics, and my students don't at this point of the semester. So I think it's fair for me to talk more with you than I would with my students, although I'm going to give you lots of times to get your hands dirty, if you will, on the types of activities that I deal with. We're going to be looking at the activities for analyzing data, and you can see the 4 listed there. If there's time left over, we'll do some others at the end. And you can see lists for the other sessions as well, and then some brief list of references at the end. How about if we go ahead and jump in? If you turn to the 3rd page, let me set the stage for where this occurs in my course. It's in the first 3 weeks of the course where we're dealing with exploring data, exploring distributions of data. Students have seen what data is all about. They've looked at variables, categorical variables, and measurement variables. They've looked at various graphical displays, such as box plots and histograms and stem and leaf plots, the standard fare. They've also looked at numerical summaries, both of the center of a distribution and of the spread of a distribution. This is the point at which they first compare distributions of data between 2 groups. And the example here, it's real data. The percentage growth in population for each of the 50 states between 1990 and 1993. And you might well be thinking, well, I don't see 2 groups there. Well, I'm going to ask you to form 2 groups. I'm going to ask you, just as I asked my students, to go through and categorize each state according to whether it's east of the Mississippi River or west of the Mississippi River. Why don't you take 2 minutes, 3 minutes? I'll give you a hint. I'll tell you the same thing I tell my students. There's 26 east and 24 west. Of course, that doesn't guarantee that you're right if you end up with 26 east and 24 west. But I'll tell you what I tell my students.
Oh, we got a map here.
Oh, each sheet.
Sorry, Alan.
As soon as you find one you're not sure about, call it out and we'll discuss it and do geography by democracy here. How about Alabama, first of all? East. Alaska.
West.
Everybody knows one. All right, I won't read them to you. As soon as you're not sure of one, just like I tell my students, call it out, we'll talk about it. I was at a week-long workshop in Minnesota last week, and those people who live right on the river are really good at this. So when you're not sure, call it out. Don't be embarrassed.
Illinois is west, north.
How about Illinois? Illinois is east of the river. The river is the western border of Illinois. If I was smart, I'd get out my book and where I have the answers. Illinois, we decided, was east. There's 2 states that the river actually goes through, but the majority of the state is one side or the other in those cases.
Indiana east.
Indiana, what do you think? East, sounds good.
Iowa east.
How about Iowa?
Iowa's west.
Difference of opinion on Iowa.
Most of it.
Most of you are saying west. Yeah, Iowa's west. The river's the eastern border of Iowa. Louisiana, the river ends in Louisiana, of course. It actually goes through Louisiana, but most of Louisiana is west. Michigan? How about Michigan? What do you think of Michigan, folks? Michigan's east.
Oh, it must be because Detroit's on this other river. What about Minnesota?
Minnesota, the river starts there, it goes through Minnesota, but most of Minnesota is west. Pardon me?
East.
Mississippi?
East.
East, sounds good. Occasionally I'll glance down at the answers and make sure I'm not misleading. Minnesota, most of Minnesota is, have we decided Minnesota? West. That's good. You might well be wondering at this point why on earth you're doing this. Well, my point is certainly not that I want students to know geography, although that would certainly be nice. My real point is to try to convince students to have them understand as thoroughly as possible that data aren't just numbers. These aren't just 50 numbers on the page that we're going to do manipulations with. Data are numbers with a context collected for a purpose. So I'm trying to engage students with the data. It might not be data that inherently interests them, but by getting them to talk with each other, to debate which states are where, hopefully it engages them with the data and makes them see that these aren't just 50 naked numbers on the page, but numbers that have a context that we're going to look at with a specific question in mind. The question we're leading up to is whether eastern states or western states tended to have higher percentage growth in population in the early 90s. So we're really getting at an important statistical principle here, the idea of a tendency. What's it mean to say men are taller than women? Doesn't mean every man's taller than every woman. There's a tendency for men to be taller than women. Most men are taller than most women. If you look at measures of center, the measure of center for men is higher than that for women if you're looking at height. That's the type of statistical idea that students are supposed to get out of this activity. And also along the way, we're going to meet one important graphical display, the side-by-side stem and leaf plot, which is what's coming up in a minute here once you get these states categorized. How about Wisconsin? Wisconsin?
It better be east or I'll
Better be east.
24.
East
I'll
works.
get 24.
Wisconsin's east. Should end up with 26 east, 24 west. If you don't get it exactly, we're not going to spend the whole hour making sure this works out right. Just get it close. When you're done, then turn the page, please, and see what I next ask students to do, which is to take these 50 numbers, these 50 observations, and create a side-by-side stem plot with them. Makes sense if you've ever looked at a map to put the western states on the left side of the stem plot and the east on the right. And the easiest way to go about this, of course, is to take the states one at a time. Take Alabama's 3.6% change and go to the row where the stem is 3 and put a leaf of 6 on the appropriate side. So Alabama, we decided, was east or west. Alabama's east, so we'll put a leaf of 6 on the row where the stem is 2. So why don't you take a few minutes and go down the list, please, and indulge me and create the side-by-side stem plot. So Alaska's next, 8.9. Did I do that right? So Alaska's 8.9. We'll put a leaf of 9 to the left of the row where the stem is 8. And again, don't worry about getting it exactly right, but do enough that you get a sense for the general distribution on both sides of the country. Arkansas is east of there. Yeah.
No, Arkansas is west.
I got the answers here.
Did you go right from Texas into Arkansas?
Oh, you're right. Arkansas is west. I'm sorry. Sorry. Gee whiz. Gonna send me home.
I guess I'll cheat too.
If you really want to cheat, I've got the answer, quote unquote, on the board. It's more fun to experience it like a student.
This is your rough work. Then you would go into 331.
How about if I give you 30 seconds? If you're not quite done, that's fine, but let's move on in 30 seconds.
This is your rough work.
Yes, ma'am.
Side by side semi plot, which you get to put down all the other stuff you put on the regular semi.
Depths and things like that. Yeah. One could.
You could put it on either side.
You could put it on either side. Yeah, I usually don't bother to do that. Okay, how about if I interrupt you, please, and let's talk about what you found and look at the remaining questions on the activity here. You'll notice what I ask in question C is for students to remember what they learned a couple class periods ago and calculate the median value of the percentage change in each region. So I wouldn't, again, with my students, they'd be working on these activities. I'd be wandering about the room, making sure they're on the right track, asking them questions, answering questions. But how about if we do this together to save some time here? What's the median percentage change in the East? We've got 26 eastern states. So how are we going to find the median?
If they're in order, count down 13.
Yeah, we've got them in order. That's one nice thing about the stem plot. So we've got an even number. We need the average of the 13th and 14th, which is where? Pardon me? Yeah, 2.3 and 2.7 are right in the middle. So the median percentage growth for an eastern state in the early 90s was 2.5%. And for the West, we've got 24 of them, so we're up to 12th and 13th. Somebody help me out, please. 5.1 and 3.7. What's that, 4.4? Next question. Next question is a detour again. Identify your home state and comment on where it fits into the distribution. It certainly doesn't get at what I said was the idea here of looking at the idea of a tendency, comparing the two distributions. But again, I'm trying to get the students to stop and reflect and think about these not just as 50 numbers, but as data, and to personally identify with it. So if you're from Nevada and you see that your state by far had the biggest percentage growth of any state in the early 90s, then that's worth looking at and commenting on. If you're from Connecticut and you only had, you actually lost population in the early 90s, that's worth commenting on. Trying to get, pardon me?
They went to Nevada.
They went to Nevada. Could be, could be. Better get. There's gambling in Connecticut though, so that's not the reason. That's true. So again, the point of D seems a little beside the point, but the point again is to try to get students to personally identify with the data, to care about the analysis, to see these not just as 50 naked numbers. Finally, in E, we start to get at the real issue here. Does one region tend to have higher percentage changes than the other? What do you think? Just looking at the shape of the distribution. Yeah, the West tended to have higher percentage changes in the early 90s in terms of population growth than the East did. So I look for students to say that and to write a sentence or two about it. How about question F then? Is it the case that every region, every state from the West had a higher percentage change in population than every state from the East? Certainly not. We can find lots and lots and lots of pairs where the eastern state had a higher percentage change than the western state. Take whichever one had the 6.8 and you've got your choice of lots and lots of western states to pair it up with, and that's an example that bucks the trend. So trying to convince students or have students discover, if you will, that statistical tendencies aren't hard and fast rules that hold in each case. They hold most of the time. They hold on the average. Throw out your favorite buzzwords to describe the situation there. Another way of thinking about it is what question G tries to get at. If you were to randomly pick a western state, randomly pick an eastern state, which would you expect to have the higher percentage change? You wouldn't be guaranteed, but most of the pairs would have the western state with the higher percentage change. So the point of the activity is pretty much threefold. One, just to give students some real data and engage them in it, to get them to care about it, to talk about it with each other. More importantly, to introduce a specific technique of side-by-side stem plots that are efficient and widely used. And perhaps more importantly still, to start to lay the foundation for this concept of a statistical tendency that comes up over and over and over again when studying statistics. And I just went through this with you in probably 3 times the speed that my students would go through it. But again, they would be working on these questions, talking with each other, just as you did. I, as the instructor, see my role as walking around the room, looking over shoulders, being proactive, not waiting for them to ask me questions, but going up to them and saying, why did you say what you said to E? Why did you say the West tended to have higher percentage change than the East? Explain it to me. And confronting students with that kind of relationship. Questions, comments on the...
Yeah, how big is your class?
I'm lucky. My class is limited to 24 students. And we meet all the time in a computer classroom, so when we need the computer, it's always right there. When we don't, like with this activity, then we just ignore it, just as we've just ignored it. Only have 12 computers, so students pair up, but that's almost an advantage in that it gets them talking to each other, necessarily. Yeah.
Do you specifically have the computer lab aside from the classroom session?
Pardon me?
Do you specifically have a separate computer lab, staff computer lab, aside from the statistical class?
No. The lab is available to them outside of class in the evenings and things like that. And it's almost exclusively a residential college, so that's pretty convenient for them. But all the class meetings are held in a computer-equipped classroom. So when we need the machines, we have them. When we don't, we just ignore them.
What would you say is the advantage of doing this exercise in class as opposed to having them do it on their own at home?
That's a good question. Just the fact that I have some control over it, I make sure they have access to the right answers. I make sure they have a chance to ask questions of me. I think it would be useful for homework also, but I think there's an advantage to taking class time to do this kind of thing.
One which states are east and west.
Yeah, that might be not the best use of class time, but it does get them talking to each other and thinking about the data.
How much would you talk about, statistical tendencies when you're doing? Would you just have them answer this question, kind of discover for themselves, or would you direct them?
I do that, and right, exactly. I talk more at the end. My goal is to have them engage in activities that introduce the idea before I talk about the idea. So that hopefully they've confronted the questions themselves, maybe come to some conclusions, maybe not, but if they've thought about the issues themselves before I talk about it, I feel that they're able to connect with what I have to say about it.
Do you have a sense of how many of your students have their own computers?
Lots of them, probably more than half do, but I doubt if more than, very few have Minitab and access to Minitab outside of the computer-equipped classroom. So most of the time when they're using the computers, it's during class time, and they come back to the same room in the evening.
Primarily probably PCs with Excel, though.
Yeah. I happen to be in a Mac classroom, but that's not a big deal, of course. Huh?
Do you give a lot of the students ahead of time so that they can really read before they come to the
They
class?
can if they want to. It's a whole book of activities, and they purchase the book ahead of time. And I used to worry, and sometimes people ask me, there is scattered through the book exposition that explains what they were supposed to have learned, as well as the activities. So sometimes I get asked, well, do you worry that students will read ahead and learn what they're supposed to learn on their own? And for a while I worried about that, and then it occurred to me, if that's my worst problem, that students are reading ahead and learning before I want them to, then I've got other things to worry about.
Two questions. You mentioned the book that you get. Is that book you wrote, or the book that's available? And secondly, do you make use of the Chance database?
I don't make use of the Chance database as much as I could or should, and it's certainly an excellent resource. Yeah, the book I'm talking about is Workshop Statistics, which I wrote and is available. How about if we go on to the second activity? This one's a little bit later in the course, another week or so later, where we're starting to look at bivariate relationships for the first time and the idea of association. And again, association is a kind of statistical tendency. Just because taller people tend to weigh more, that doesn't mean that if I'm taller than you, that necessarily I have to weigh more. And that's the kind of idea that students are supposed to get out of this activity. As long as, again, the mundane, if you will, graphical display of a scatter plot, very useful little graphical display for displaying the relationship between two variables. These are data that we'll collect on ourselves this time. I've given you a list of the point value of letters in the Scrabble game. What I'm going to ask each of you to do is figure out how many letters are in your last name and what's the Scrabble point value of your last name, calculated by figuring the number of points per letter and then adding them up over the number of letters in your name. Couldn't say that very well, but I think you understand what it means. So my name, Rossman, has 7 letters. They're all boring little 1-point letters except the M, which is worth 3, so I've got 7 letters and 9 points. One of the rules that I've developed that I'm about to violate is to always have students submit data confidentially. So even the most innocuous question, I've had very embarrassing moments when it turned out that a student, for very good reasons, didn't want to admit to the class what his or her values on that variable were. So having said that, though, I'm about to violate this, and I hope no one's embarrassed to report the number of letters or the number of Scrabble points in the name. Why did I write 3? If you don't mind, let's just go around the room and I'll ask you how many letters and how many points.
7 and 10. 5 and 9. 6 and 9.
8, 12.
10, 29.
10 and 29, thank you.
9 and 17.
9 and 17.
Is there a prize?
First one out the door to lunch.
Well, I know.
Yeah.
6, 7.
Thanks.
8, 18.
Thank you.
5 and 6.
Thanks.
6, 12.
Thank you.
8 and 16.
Thanks.
I'm sorry. Please change mine.
They tell me to, I
It's
will.
more than that.
Oh.
Yeah.
All right.
15. So I have to go back there because I have repeat. So
Okay. Why don't you get back to us? I'm really wrong.
6 and 6.
Thanks.
10 and 19.
Thank you.
6 and 9.
Thanks.
7, 15.
Thanks.
6 and 8.
Thank you.
7 and 12.
Thanks.
7 and 9.
Thank you.
5 and 7.
Okay, thank you all. You have been still working? You can go ahead and record those if you'd like. And what I'll ask you to do is what I ask my students to do, namely create a scatter plot here. And certainly we could turn the computers on and have Minitab do it. If you want to, that's fine, but I try to have students do small scale displays and calculations by hand first, so that they won't just see the computer spitting out these displays and these dots without any connection to the observations from which they came. So this is small enough that if you'll indulge me, why don't you take 3 minutes and create the scatter plot here, please. I've given you the axes. I don't know if the axes go far enough.
I missed, wants to do it by hand or move it?
If you're familiar with Minitab and would rather turn to Minitab, that's fine. If you want to just do it by hand, that's fine too. Probably be about equally quick. Very fine. That's not even a double or triple word score. Don't worry about getting this real careful, exact. Get the general idea. Once you've got the scatter plot, why don't you go ahead and turn the page, please, and answer the ensuing questions. We'll talk about them in a couple minutes.
I don't do. Yeah.
Actually, that's the.
Yeah, right. Right, right. I have no idea.
That's true. That's keeps it.
Yeah. Right, right. No, and I've been able to study this.
Oh, yeah, when you've done that,
Yeah.
you got that.
Right.
Yeah, I'll.
So now the beauty of doing this kind of stuff, like to be able to see this stuff, it's just a different way of visualizing data.
So now we see, okay, go voting stats. Click on stat menu. Go to progression. Oh, see, fit it line fine.
Okay.
Okay, shall we talk about what you found out here? If you don't have your scatter plot quite done, you can look at my horrible excuse for a scatter plot on the board there. I told you not to take your time to make it real neat or anything. So point 4, you circled your own point. Again, just trying to get students to personally identify with the data to see where they fit in terms of the distribution. In this case, in terms of the distribution both on each individual variable and on the bivariate relationship there. Of course, point 5 is starting to get at the real bivariate question. Do the points seem to follow exactly according to some mathematical relationship? Well, roughly. It's certainly not exact, but there's certainly a relationship here. Do the points seem to be randomly scattered about? Now, they aren't just randomly scattered about, but they're not also not exactly on a straight line. They're not on an exact parabola or anything like that. Somewhat something in between, right? And that's what question 7 is trying to get at. Is there a tendency for people with more letters in their last names to also have a greater point value in their last names? And yeah, there's certainly an clear upward trend there, even without the outlier. It's a tendency for people with more letters to have more points in their names. How about 8? If one person's name has more letters than another, is that person guaranteed to have a higher Scrabble point value than the other? No, right? We can find examples where A has more letters than B, but A has fewer Scrabble points than B. Can you find one such pair for me, please? There's a 5, 9, and there's a 6, 8. So that certainly works, and we could find other pairs as well. So again, the idea of a statistical tendency that it holds in general, holds in most cases, but it's certainly not a hard and fast rule like mathematical relationships tend to be. Which is what question 9 tries to return to. If one person's name has more letters than another, is that person likely to have a higher point value than the other? It's getting students to think about that issue, write a few sentences about it, explaining it in their own words is the real point here. Along again with the specific technique of a scatter plot for displaying two variables simultaneously and the relationship between them.
It seems like a numbers 5 and 6, though, using the words exactly and completely guarantees a no answer.
Yeah, that's true. Which is it's sort of what I'm looking for, that there is some ambiguity and some fuzziness here. Perhaps I do nothing more than condition students that when they see such words, they answer no. I hope that's not the case. Questions, comments here?
When you do these classrooms with these activities in your classroom, then do you do as you do with us, sum together? And
I try to, yeah.
Like get the data? Exactly.
Yeah. Certainly data collection, we do much like that, except I gather it on sheets of paper to protect their anonymity. I try to hold wrap-up discussions like I've done with you. That's a little more difficult because they move at such different paces. And I don't want to hinder the students who are moving more slowly. And I also don't want the students moving more quickly to feel like they have to sit there and talk about basketball for 10 minutes while the others catch up. But I try to have wrap-up discussions.
Now, are you finding that students are at all hesitant to do these type of activities in the classroom, or are they like learning faster, retaining better, or?
My students aren't hesitant. I'm not sure why. I've heard other people say that their students are hesitant, that they feel the instructor isn't doing his or her job by teaching.
Right.
I certainly try from day one to sell them on this is how it's going to be.
Right.
And there's lots of research and experience that indicates that this is a legitimate way to learn, if not a better way to learn. And trust me, and they're a very trusting group.
Good.
Shall we continue? Activity 3, we won't spend as much time on the hands-on aspect. This is designed to make a very specific, important point with regard to statistics and drawing conclusions from numerical information. Real data again, somewhat unusual data taken from the World Almanac. For these 22 countries, what you see listed before you is the life expectancy for the country and the number of people per television set in the country. Kind of a strange variable. Think about that for a minute. People per television set. I'm going to try to get Minitab to help out with this. I hear it click.
It does take
You're doing something. I've got these data entered into Minitab, and if you're comfortable, well, actually, I'd rather you didn't take your time to enter them into Minitab. That would be too time-consuming. Let's look at the questions that I asked the students, and I'll ask you. First question, again, you'll notice doesn't get at the real point here. First question is just to stop and think and look at the data, and don't think of these as just numbers on the sheet. Which of the countries listed as the fewest people per television? Where would you look first if you weren't going to look through all 22? The United States, 1.3 people per television as of 1990, according to my World Almanac. Which has the most people per television? Haiti, 234 people per television set in Haiti. Okay. Let's use the computer to do what one should do first with bivariate data. Look at a scatter plot of the data. And I can get Minitab to do that by going under the graph menu and choosing plot and asking for a scatter plot of life expectancy versus people per TV. How do you think it's going to look? Actually, earlier in the class, the very beginning of class, students fill out what's called a preliminary section where I ask them to think about what's going to happen that day. So I would have already asked them, do you think that there's any connection between these two variables? And if so, what kind do you expect to see? What do you expect this scatter plot to look like?
I would expect there to be a correlation.
Do you?
Because usually, not always, but usually those countries that have a lot of technology have also better medical facilities.
Okay.
But that doesn't necessarily mean that the TVs are causing it to live longer.
So do you think this is going to look negative or positive, this association? Careful though, it's people per TV.
Right, negative.
So you're expecting negative. And
Did you enter the first one down there? Where's that block?
I think it's the, I think that says 44, 200.
Yeah, it says two something. Okay.
Is it just being slow?
No, it's,
Yeah, they're very slow.
Okay.
Yeah.
Sure enough, it looks pretty negative. Certainly not linear, but that there's a clear association here. Just as you said, countries that have many people per TV, i.e. low technology, tend to have lower life expectancies. Places that have few people per TV tend to have higher life expectancies. So that's what students are to answer in the next couple of questions. We skip down to, well, B asks them to explain the relationship that they see in the scatter plot. Skipping down to D, since the association is so strongly negative, one might conclude that sending TVs to countries with low life expectancies would cause inhabitants to live longer. And you know that's ridiculous. My students know that's ridiculous, and they're very quick to tell me so, and to write a few sentences explaining why it's ridiculous. So the point, of course, is a very specific one. The correlation is different than causation. But just because two variables are strongly associated or strongly correlated does not, by any stretch of the imagination, mean that one can infer a cause and effect relationship. But instead of me writing that on the board, instead of me telling students that, I used to even use the mathematical symbol and say correlation does not imply causation. Who knows if they had any idea what I was saying? My hope is that by discovering this quote-unquote for themselves in a very rigged setting, real data but a ridiculous setting nevertheless, my hope is that they'll better remember the principle and understand the principle and be cautious about not misapplying it when they analyze data for themselves or read about other people's analysis of data for themselves. Also gives me an opportunity to introduce the idea of a confounding variable and ask them to come up with explanations for variables that are really behind the cause and effect here, that are confounded with both life expectancy and people per TV. And they're very good at pointing out the types of things you mentioned, level of technology in the country, general level of sophistication and quality of life in the country, and things like that affect both life expectancy and people per TV. Huh?
Did you ask them to guess at what the value of R would be for there and then pull it out?
Often I do. I think in this case maybe I didn't, but it's certainly a good idea. Yeah. This isn't the best example to deal with correlation coefficient at all, since it's such a nonlinear relationship. So what I really have in mind is just the nature of the association, and that association is different than causation with this one. Questions, comments? So this was, I think of this as an activity in that students are answering questions and doing analysis and trying to discover principles for themselves. It's not an activity in the same sense that the previous two were, where we gathered data or where we sorted and manipulated data ourselves. The students are still addressing the questions on their own, doing the analysis, trying to explain what the statistical moral, the story, if you will, is. So in that sense, I consider it a hands-on activity.
In the computer room, is the computer room something like this one?
It's not as nice as this. We don't have the recessed computers.
Oh, okay.
We have Macintoshes, 2 per student instead of 1 per student.
There's room to write and stuff?
There's enough room to write. Yeah, we were careful in how we laid out the tables to make sure there was room to write. Chairs are on swivels so students can swivel around and talk to the people behind them or in front of them as well as with their partners.
Just curious how you teach in a classroom like that where people seem to want to play with the keys and,
Send
fool around.
email.
Exactly.
They-
Do each other.
They do a pretty good job of staying on task. Certainly not always, but playing games and sending email is not much of a problem. Well, actually, that's an advantage there of not having the recessed monitors, because it's very easy for me to stand in the back of the room and see what's on everyone's screen. And they realize the class time is when you learn the stuff, and they're smart enough to take advantage of that. Most of them. Certainly there's exceptions. One tangible benefit of this change in pedagogy is that students come to class much more often. Attendance is much better because they realize you've got to be there to do the activities. It's your chance to ask questions and get immediate feedback. And again, I realize I have a luxury of having only 24 students, and I can afford to do that.
I assume that you have homework assignments in addition to these classroom activities. Are students as motivated to do the homework assignments? Should they do as well?
Well, they're graded on the homework assignments. I used to also grade them on the in-class activities, but that just got to be too much of a task. So I don't grade all of the in-class stuff anymore. When I was writing the materials, it was very helpful to see firsthand what they were writing. But I'd still like to be able to do that, but there's just not enough hours.
I just had a comment about this exercise. I really like this. I think this is so important because it has so many applications, not just to statistics, but to many different things. Because how many times do you turn on the news and they automatically assume there's a correlation, there's got to be a causation. And this is such an important thing to teach the students. I like this.
Thanks. One more activity on your sheet, if you'll turn there, please. Hypothetical data this time, but realistic data, and that the phenomenon you're going to study here comes up in similar settings. This is a couple weeks later in the course. We're still dealing with bivariate relationships between variables, but now we've moved from relationships between measurement variables to looking at relationships between categorical variables, so analyzing two-way tables. And I think without further ado, I'll just give you 5 minutes to please work through this example. You'll want a hand calculator for some of the calculations. If you don't have one, you can use Minitab as a hand calculator, or there's probably one somewhere else on the computer, but I'm not a PC person, so I'm not the one to tell you where to find that. If you want to get into Minitab, you need to go into the mathematics folder. Is that what they're called on PCs? There's a calculator under accessories, is that right? Okay, thanks. If you just want to set up the fractions and let someone else do the calculating, that's all right too.
Calculator or using the Minitab? Oh. Yeah, I'll do is a division then. So far.
I trust you're not like my students and want a calculator for part A.
Okay.
Yeah, so for students. Take up. Because you're trying to get that work here when you're fine. So, well, that's what most do. So, right, like a few students are.
Okay, shall we talk about what you're finding out here, please? Somebody please tell me what you found overall. What was Hospital A's recovery rate overall? 80%, and Hospital B, 90, so which is higher? You can do that. B looks better. B saves 90% of its patients. A saves only 80% of its patients. When we break it down according to whether patients were in good or poor condition to begin with, first of all, I hope you checked my arithmetic and made sure I wasn't pulling one over on you. 590 plus 210 does in fact give you 800, and so on with the other four cells. So for those in good condition, Hospital A saved what percent? 98, and B 97 or so. So A is a little bit better. They're both awfully good. If you come in good condition, great chance you'll survive. But A does a little better than B. How about those in poor condition? A has, and B has. A does better there too. So of course the natural question is what's asked in E. How in the world do you explain this? How does it happen that B does better overall? And when we break it into two categories, A does better within each category. Yeah, exactly. Everyone hear that? Believe that? The key is that A treats more patients in poor condition. If you look at the raw numbers, which aren't on the board here, A has 400 poor condition patients, B has only 100 poor condition patients. That by itself doesn't explain anything, of course, until you couple it with the obvious fact that those in poor condition survive less often than those in good condition. Of course, this is the phenomenon known as Simpsons Paradox, that the direction of the proportions can reverse when you break it down into further subcategories. And I like this example as a motivating, as an introductory example, because one of the two conditions is transparent here. Simpsons Paradox, I tell students, always involves two different things going on. But here one of them is obvious. The obvious one is that those in poor conditions survive less often. That's natural to anyone, just about. So all you have to see from the data, all you have to garner from the data, is the fact that A treats so many more in poor condition than hospital B does. So when you do the weighted average, then it turns out the way it does. I used to start with the famous Berkeley data. Are you familiar with that? The data from the mid-70s when the University of California, Berkeley, was charged with sex discrimination in its graduate admissions. Because if you look at the acceptance rate for male applicants, it was about 45%, and for female was about 31%. When you break it down program by program, they're very equitable within each program. And if anything, most programs admitted a higher proportion of women than men. And the explanation is, again, Simpsons Paradox. For whatever reason, men were applying in very big numbers to the easier programs to get into. Women were applying in big numbers to the much more difficult programs to get into. So that's why when you do the weighted averages, that men had a much higher acceptance rate overall, even though they didn't within any one particular program. So it's a good example of a couple things. First of all, Simpsons Paradox is kind of neat and fun, and students enjoy it because it is counterintuitive. More importantly, it talks about the value of gathering more data, of gathering information on more variables, and doing more sophisticated analyses on more variables. And also, it's a reminder that I come back to later in the course to convince students that you can't draw cause and effect conclusions from observational studies. Since the hospital data, they're hypothetical anyway, but the way it's set up, it's an observational study, as opposed to having done a controlled experiment, in which case you could have expected the various conditions to balance out between the two groups, and you would have had more ammunition for drawing a cause and effect conclusion from anything that you might have found. Questions or comments for me? And again, the rest of the handout deals with activities involved with studying randomness and then statistical inference. And I invite you to peruse those at your leisure. I've been going a little less than an hour, but time is officially up. Be happy to take any questions or comments.
How long have you been doing this?
About 5 years now. Yeah. I certainly enjoy it. Students seem to enjoy it. Of course, enjoyment isn't the bottom line. The bottom line is whether they're learning. And my gut reaction says that there is, but I haven't gotten to doing real thorough studies on that. And I don't know if I ever will. There's so many hours in a day and so many things to do.
Do you, as Dr. Moore was talking about, you find you have to cover less material?
Definitely, yeah. It's a trade-off I'm willing to make. Like I can tell you what I've cut out if you want to hear it, but it's certainly a trade-off I'm willing to make. In the context of leading to statistical ideas like confidence and significance. And we do a lot of explorations through simulations to get at those ideas. Still talk about normal distributions and reading a normal table, but that's as much probability as I cover. I love probability, don't get me wrong. I love teaching a sophomore level calculus-based course in probability. It might be my favorite course. But I've only got 14 weeks and I want to do activities and have self-explorations, and so I was happy to jettison that. Don't get into as many inference techniques as lots of people do. We do get into t-tests and two-sample t-tests. Don't quite get to chi-square tests. Don't do inference for regression. Again, those are all fine things, but that's a trade-off I'm willing to make at this point.
At this point, though, are you getting through all 21 activities?
I get through all 25 activities, all 25 topics in the book, yeah. I do inference for population proportions first pretty thoroughly, and then at the end get to t-tests and t-intervals for means and comparing two means. But I do get through that.
You have them working in pairs.
They naturally work in pairs because there's two per computer here. I don't discourage them working with bigger groups, but they tend to congregate in pairs.
I found it just now that I was having trouble concentrating on the very simple math because of the noise in the room.
Yeah.
Is that, I mean, it's like, 100, 30 out of 100 is enough. There's so much noise I was having trouble. Is the noise flashing very loud?
It's not as loud as this for some reason, just because they aren't as engaged and as friendly and talkative. And students certainly haven't complained about that. I don't know if they're better at tuning out extraneous noise than we are or what.
Am I the only one that had that problem?
Anyone else have noticed that? Difficulty concentrating with the noise?
Thank you. That's just the background noise.
Other questions or comments I could feel?
Are any of your homework assignments done in groups, or is it all individual?
It's handed in individually. I encourage them to work in groups, but I grade it individually. I tell them to please write it up in your own words.
So what is your percentage there, how do you come up with your final grade? What percentage?
Somewhat traditionally, I give 3 exams, and each exam counts 30%, and the homework altogether counts 10%.
Do they do the exams?
No, I give them output and ask them to interpret it and draw conclusions from it and explain their reasoning and all. My goal is to have at least half the exam not be computational. I have varying levels of success with that.
You're doing a talk, I think this afternoon, on looking beyond the formula for information, which,
That's not me.
that's not you?
No.
You're Rossman, I'm sorry.
That's all right. Now, I'm going to be doing exactly what's in the handout for the rest of my time here. Yeah. So the spirit will be exactly like this, but we'll talk about sampling distributions this afternoon, and we'll talk about inference tomorrow morning.
And with your students, with the computer, like in the classroom, do you anticipate in the next few years, are you going to have them turn in these classroom assignments or homework assignments on like email, or are you anticipating any of that?
I haven't anticipated it yet, but that might come to pass.
Yeah, I had a tremendous resistance to non-computational type questions. If you could share something on that, you mentioned that you mixed results with that.
I have mixed results in terms of my own ability to write good exams that aren't computational. I try to ask lots of questions, like in the inference portions, do the usual confidence interval in A and interpret it and explain how it relates to the context of the study. But then question B might be, if the sample size had been 4 times larger, without doing the calculation, tell me how the interval would have changed. Or if the population of interest had been all Pennsylvanians instead of all Americans, tell me how the interval would have changed or not, and explain your reasoning. So I try to ask questions like that build on the computations, but the one can do in principle without being able to do the computations at all. Lots of, explain and interpret, and what recommendation would you give the researcher who had brought you these data to begin with? Questions like that.
Does your course involve any certification with respect to computer techniques and skills?
Certification, nothing formal.
Examination or requirement working back, does their grade imply that they are computer literate for statistics?
Probably not. They don't do the exams on the computer. So if one understood all the ideas, could do the calculations, could interpret and explain well without being able to use the computer to do statistics, one could probably, in principle, succeed, but I don't think that happens. I think it's the ones who are keeping up with the homework, who are able to use the technology well, do well in the course anyway.
Do they get instruction elsewhere in other courses with respect to computer skills?
Throughout the curriculum, they're using the computer almost in every course. In many courses just for word processing, but for spreadsheet applications in many courses, statistical analysis package in some courses. The rest of the math curriculum, we're using computer algebra systems and other software.
And do you give them specific instruction with Minitab?
Yes, yeah. At the first day or two, I go over very, very clearly with them exactly the basics of it. I project and have them follow along. After that, though, I try not to project and have them follow, but rather have them do lots of hunting and finding themselves. What I do is at the beginning of class, I'll write on the board what they have to know for that day. The first time they use a scatter plot, I just do this to tell them that you can find scatter plot in the graph menu and you can figure out the rest from there, and that's as much as I say. And then as I walk around, the ones who are having trouble, I obviously give them the help. Students are pretty good, I've found, at using the mouse and hunting and finding things.
Do any of your other departments require that their students take this course?
There's a
as part
few,
of
yeah.
their-
Economics and policy studies, and there's a few
And
like that.
do they sort of have demands on what they want students to know? For example, in our sociology department wanted our statistics course to cover know the techniques, but that's getting kind of difficult for one semester course, so much we go through.
Right.
Don't want that.
Yeah. They haven't complained to me, I guess is the answer. And if they did complain, I would try to argue that if students really understand the basics of inference and of drawing displays and creating numerical summaries and thinking a lot about data collection and issues like that, and then the underlying principles of inference, if they know all that, they should be able to interpret ANOVA output pretty well with minimal instruction from them. So if I got that argument, that's what I would try to respond with, and probably would have little success, I don't know.
Well, maybe we should save any other questions for our lunch hour, which is coming up now, so thank you very much. So we have some MCC people here who can help me lead everyone to lunch. Basically, we go up a long turn right.